uninteresting stuff. All right, so there is no guest speaker, but I will talk about the news. And let me move this down here. All right. So that's pretty interesting. Several of these were good. And this one particularly relevant to this class. All right, so Facebook is going to have a Supreme Court. This is they're constantly trying to do something about content moderation. Everybody is very angry about objectionable stuff on Facebook, and every time they try to do something about it, they end up taking on the wrong stuff and just making people more angry. So their latest plan is to create a Supreme Court to handle takedown requests. So we'll see how that turns out. Everyone's been talking about supply chain attacks a lot these days. Aha, this nonsense is happening again. I think a student once figured out how to make it stop doing this. This is Zoom. Annotate clear all drawings. Ah, good, all right. So anyway, so supply chain attacks are really big, and this is happening in Saudi Arabia, but it'll happen elsewhere. They're hacking IT providers so they can then hack their customers, which is a pretty good trick. It happened here to, I think, Target. They came in through the heating, ventilation, and air conditioning system. And now if you have any kind of IT provider, they have a login into your system. So it is a good way to come in. And this is a huge issue. Your business partners have access to passwords and access to your systems. And so if they get hacked, then you'll get hacked. So this is kind of incredible. I didn't know it was this bad. Of course, Lyft is amateurs driving cars, so they could be crooks. So this woman got raped, and then she sued, and there are 14 other women suing for the same thing. And apparently, if you get raped in a Lyft vehicle, they will still make you pay for the ride, and they will not fire the driver and let him continue driving for 2 years. And they don't have any background checks. They don't take fingerprints, and they don't do anything. They don't even forgive you for the cost of the ride. So apparently these lawsuits are to get them to upgrade. I had no idea it was that terrible. So obviously it's a good idea to sue. And this is pretty shameful. This is particularly relevant to this class. We're going to be exploiting a lot of vulnerabilities, and this rates how hot they are. Some company has decided to determine how common these vulnerabilities are and how severe they are. And here's the top 10. These should all be pretty familiar. Buffer overflows, still #1, which surprises me. That's the one we do mostly in this class. But I know Microsoft, about 4 years ago, published a list of how popular these are. And they said buffer overflows were no longer a large percentage of Microsoft exploits. It's now mostly dangling pointers. But that's coming up. Cross-site scripting. And then here's SQL injection. That's always big. And use after free. That's dangling pointers. That's the one that Microsoft said is now #1, but these guys regarded as #7. Yeah.
Is the buffer overflow a denial of service, or?
Well, they can all have different levels of severity. You can use them to create a denial of service, or sometimes you can use them to get remote code execution. Okay. The vulnerability does not determine how severe it is. The context around it does. For example, a lot of web pages have SQL injection, but it's in a minor database with nothing important in it, so it doesn't have much consequence. And that's the big issue. But anyway, that is a very good question. And directory traversal is still around. Boy, I thought this was gone 10 years ago. The main implementation of this I see these days is PHP, path traversal, where you can take a PHP file name and put in a path and refer to another file. So anyway, there's more of them, but these are all famous old integer overflows. It's interesting stuff. And so apparently these old-fashioned techniques I'm covering in this course are not as out of date as I thought. I thought buffer overflows would not even be in the top 10 anymore, let alone #1. Anyway, so encrypted DNS is a big fight. They're now going to put it in Firefox and Chrome. So your DNS goes over HTTPS. First, you make a TCP connection to a DNS server, then you make an HTTPS encrypted connection, and then you resolve all your domain names through that. Now, I think of this as a gigantic step forward. Right now, DNS resolutions are done with unencrypted UDP traffic on your local network, and often they continue in that form all the way to a remote server, so you're broadcasting to everybody, every website you go to. And that's handy for people who want to spy on you, like your network administrator and the government, but it's certainly bad for user privacy. So this seems like a very good idea, and several groups have come up to scream bloody murder about it, and I think they're just confused. Now, the people that have complained justifiably are people who want to filter content on company networks or on national networks, because of course, if you encrypt the DNS traffic, you cannot read it, so you can't filter it. And I know there have been some plans to filter content, like to block porn based on the domain names. You'll have to block it another way. You could still block it by having a list of forbidden IP addresses, which would be a better way to do it. But anyway, but other people are protesting this. The European group is complaining that it is going to expose all your traffic to Cloudflare, and Cloudflare is an American company, and that's terrible. But almost all DNS resolutions take place in America anyway. It's anyway. I think that makes no sense at all. To say that it makes you less private because your DNS queries go to some resolver somewhere seems to me to totally miss the point. They're already going to a resolver somewhere, and they're doing it unencrypted. But anyway, this is coming. It's going to be built into Chrome and Firefox soon, and Burp already uses it, and I think it's a big step forward. But various people are screaming and yelling. The only ones with any justification, I think, are the ones that want to filter traffic. Anyway, so here we are. The guest speaker didn't come, so I want to talk about Heap Overflows, and that's going very well. I got it set up to go here, and there was a project on this one I was unable to get working when I moved to the cloud on the way to China, and I finally got it working today, so that's good. So we got the proper 2 projects there should be about Heap Overflow ready to go. So here we are. Let me get rid of this and make that big. Right. So we'll talk about Heap Overflows. So the heap, we've talked previously about the stack, and the stack is an automatically generated region of memory. Every time you call a subroutine, it creates a stack frame, and it uses the extended stack pointer and the extended base pointer to indicate its limits. And it's used specifically for certain kinds of data. And the thing that makes Stack Overflows so easy is that at the end of every stack frame is a stored return pointer. And if you overwrite that, that goes into the EIP. So you gain direct control of the program counter and direct control of the machine. The heap is used in a much less organized way. This is where you store temporary data that you're going to use and then throw away, so you don't have to hog up as much memory. So you can see if you do info proc map in GDB, you will see there's a stack down here and there's a heap up there. And the heap is just a doubly linked list of chunks of data of various sizes, and each chunk of data has a pointer to the next chunk and a pointer to the previous chunk. And you can allocate a section of heap for use, and then you can free it later, and it will patch up the list. And that's what you should do if you have a program that consumes anything that takes up a lot of memory. Like you might have a program that handles network transmissions, so you want to do something like download a file with your program, and you want to put the file here, process it, and then clear that memory to make it available for downloading the next file, things like a web browser. Or many programs need to have temporary storage, which they then throw away, so they don't just consume too much memory. So the heap looks like this. You've got a chunk of data, and up here you've got some metadata in each chunk, like the size of the chunks, and the pointer to the next chunk, and the pointer to the previous chunk. So you can hop from chunk to chunk down this list, and that's the structure of a heap. There actually is quite a bit more to Windows heaps. Windows heaps have a thing called a look-aside list and many heaps, and attempts to deal with heap fragmentation, because of course, just like your hard drive, if you keep putting things on the heap and then deleting them and putting on more, after a while you make a mess where there's just scattered empty spaces, and you'd have to do something like clean it up. And Microsoft Windows heaps have a technique to try to put the chunks of the same size together to minimize that, and so on. But this captures the essence of it. And this is only exactly true for some older Linux-based heaps. So you can make it, here's a simple example, and this is what Project ED205 will be doing it. So you make a structure where you have a name and then a pointer. So this is a 64-character string, and this is a pointer to an object. So it's going to be a 32-bit address if you're running 32-bit code. And that's it. And that whole thing, these are 2 structures, and they are here on the heap. So here's a winner function you want to execute, and a no winner function, which you don't want to execute. And here's your main. So you allocate a data on the heap, and then you allocate a pointer on the heap. So what this did up here, this just declared these objects. It did not allocate any space anywhere. It just declared what these objects are going to be. So we created an object named data and an object named FP. And down here, we instantiate them with Malloc. Malloc is what allocates room on the heap and gives it a name D, and now you have made one object of type data, which is going to be a 64-character string, and this makes an object of type FP, which is going to be a pointer, and now you can refer to the elements of this structure with this dash greater than sign. That's the how you refer to members of a structure. This is C++, I think. Anyway, so you have a structure, and the structure has an element called FP. So here, I take the name of the structure in the FP, so I set it equal to no winner. This is a pointer to something, and it can be a pointer to a routine. So I point this to the no winner function, and down here I'm going to execute it. So it's going to print, you didn't win. And here, I'm going to copy the second argument, argv1, which is the command line argument, and put it in the name. So this is the simplest kind of overflow. I'm going to take something that came from the user and put it in name, and if the name is longer than 64 characters, it will overrun the heap, and at some larger value, larger than 64, it will eventually corrupt this pointer. So I should be able to inject characters that will change this address, and I should be able to manipulate it to hit the winner. That's the game. So let's do this one live. I've got my Debian cloud machine here. And so let me stick it over here, and let's take a look at this. Yes. Okay, so I'm going to go here. All right, so this is ED205. So I've got this program. If I let's do less ED205.c, and I'll make my window bigger. All right. So here's the program. I include libraries. I define this data and the structure and the FP. Then I have a winner function that's going to print something, and a no winner function. And down here, I got my main function that will just create them, point it to no winner, and then copy the second argument into the name. So I've compiled that, and I can run it with ED205. So if I run it like this, it tells me you have to give it a string. So I can put a string there, like hello, and it tells me the level has not been passed. But if I put in something longer, so there's 10, 20, 30, 40, 50, 60, 70, 80. Now it has a segmentation fault. So I'm able to cause it to crash. So this is the denial of service exploit, and this is the same process we always have. You have a program, you feed in data, you feed in random data until you get a crash. Now you created a denial of service attack, and the question is, can you exploit it? So you run it in a debugger. I'm going to make it quiet just to clean up my screen, 205. So I run it here. And now I can list, because I've turned on source code debugging with the -G switch when I compiled it, so you can see the source code here and work at it this way. So there's the winner function. That's not very interesting. Let's look down here, 18 to say 30. And here we have, this is still not there. Let's do list 25 to 40. Okay, so here is the allocation of space. Here's the assignment to the no winner function. This is the point where the overflow happens. So I would like to examine the heap, perhaps right after this copy. Here's where the overflow happens, and here's where it attempts to use the second object on the heap, which might have been corrupted. So I'm going to put a break before line 33. And now I can run it. I'll run it on 10As for right now. And now it's broken, so I can do info proc map, and I can see where the heap is, and there it is. So if I want to see what's on the heap, I need to examine memory near that location. And so I can do X, say 30 hexadecimal words at that location. And here I see the heap, and you can see here, here's my A's, 10 41s, 41 is A's. That's fine. And there's a whole structure here, 64 bytes long, starting here. So this is 16 bytes in a row. So that's 1, 2, 3, 4. That's 64 bytes. Then there's a couple more bytes, and these are going to be something like the size of objects and maybe pointers to the next object on the list or something. And here's an address, and I recognize this as a code address because code is always at 0804 for 32-bit code compiled here. And I can find out that, for example, by disassembling no winner. And no winner starts at 0804 84F6, and you can see it right there. So that is the pointer to no winner. It's the second object. So now you can see the story. 10 A's did not overflow the heap, but some larger number of A's will overflow this object, and I can make an exploit. So I can run this. I can do all right, let's see what that does. I'm going to put that in clipboard so I don't have to remember it. All right, I'll start again from the beginning. And now I'll look at the heap again. And I didn't hit it. See, I ran out here and I didn't hit it yet. So I need about, looks like about 12 bytes more of junk to hit it. So I can do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now I'm going to do 1, 2, 3, 4, 5, 6, 7, 8. And that some part of that will end up in the pointer. So let's run that one. Start from the beginning. Now examine the heap again. Okay, now I've overwritten everything. There's no longer any 0804 down here. So some of the characters I injected have hit it. So I can do continue. And now it ends at 1, 2, 3, 4. Because 31 is 1 and 41 is A. So this is my exploit string right here. So now I can hit any place I want to hit. Now let me have another window is the easiest way to do this. So I can leave my debugger going. And I'll make a Python attack file. Yes, they tell me there's a faster way, but this is good enough. All right, so I'll go into that directory. And I'll make attack 1. And it's going to be shebang user bin end Python. And I need missing a slash in my shebang line. Okay. And now print there. And the 1, 2, 3, 4 is what hit the EIP. So I'm going to oh, it has, I guess, a carriage return. There, that should do it. And I'm going to have up here, move this over a bit. Okay, up here, come on, it's not listening to me. Okay, EIP equals 1, 2, 3, 4. And then it's going to be print that plus EIP. So if I've done it correctly, which I'm not so sure I have, chmod all plus X A1. If I run A1, it prints a long line of junk, so it looks pretty good. Let's see if it actually does the exploit. So I run, and I want to run from the contents of A1. So that should work. Let's see if it does. Start from the beginning, continue past the breakpoint, and it does end with 1, 2, 3, 4 in the EIP, which is what this is showing. And you can find out if you want to see it more clearly. You can info registers to see the processor registers, and you'll see the EIP here containing 1, 2, 3, 4. So I now control the EIP, so I just have to have a target, so I can disassemble winner, and that's my target. I want to run this function, so I want to have that address in the EIP, so I can modify this, and I can put this, what I've taken to doing, I put it right here as a comment. That's my target. So I need to put those 4 bytes in reverse order here in hexadecimal. So it's \XCB 84 0408. So if I haven't made a mistake, this will now jump to winner and run the function. So I win. So let's see if that works. I put it in the same file, so all I have to do is run it from A1 again, say yes, and then continue. And I win. It prints level passed. So that's the, this is just like the very first buffer overflow we did, where we leak from one variable into the next variable. And that's one way to do it. So that's the simplest case of a heap overflow, where you just run from one variable into another. All right, so now we'll talk about a few other things. So the thing is, now this particular situation has artificially created a situation that's as simple as a Stack Overflow, because we put an address to a function on the heap and then we ran that function. So it created a situation very much like a Stack Overflow, where the EIP is stored right at the end of the frame. That's not normally the case, and so here's the problem. The stack always contains a stored EIP. So it's easy to get control of the instruction pointer. The heap usually does not. If you overflow from one heap object into the next, you're probably just overriding something like a downloaded file or string variable or something, which means you can do something unexpected in the code, but usually you don't get control of the EIP. But there is a situation where you can exploit the heap in more detail. And that's the point here. The whole point of using the heap is you don't want to store this data permanently until you quit the program. You want to store it, and then you want to free it so you can put other data on top of it. So what free does, if I have 3 nodes on the heap and I delete the one in the middle, to delete that, I now have to change the pointer here to skip over it and go to the third one, and I have to change the pointer in the third one to come back here. So if you think about it, I have to take an address here, and I have to do a write operation that points to an address here. So what this means is it takes information from this area and it uses it to write information over here. And what that means is if I have an overflow, and I'm able to overflow the data here and change those values, when the free operation happens, I will have a write operation where I control the data and the destination. And you'll see it live. It's quite easy to do. I can end up controlling a write operation with data I put in. I do not get control of the EIP, but I get the ability to execute a write operation in memory. And that is not hard to turn into an instruction pointer. So in fact, probably easiest if I just show you that one live. So let's get out of here and take a look at the next one, which I've already got here, which is ED206. And so let's look at ED206.c. All right, so this one here is very similar. And you've got a winner function that you want to execute. And down here, you've just got structures. Now, these things are internet structures. Something weird happened here. Let me run it again. All right, so I define this thing called structure internet that just has an integer and then a character point. Not that it's very important. I just define some object there. And now I define several of these objects. I1, I2, and I3. So there's 3 things. Then I copy the first argument into the first one and the second argument into the second one. And that's it. Then when I exit, it will free them. So the point is, at some point, it's going to free these. And if I have an overflow, which I can easily have because I put it in a name argument that didn't even specify any size, and I can put a long argument there, then I'll be able to control that operation. So if I run this one, ED206, it tells me I have to have 2 strings. So I'll run it with AAAA and BBBB. And that just prints a normal message, so that's fine. And so if I make this longer, there's 10, and that's okay. And if I put that in the clipboard and put in longer stuff like 30, now I get a crash. So it did crash for some reason. So this is the same old story. I have a program that takes input, I change the input until it crashes. Now I have denial of service. And in order to exploit it, I have to run it in debugger to figure out why. So I'm going to save that, and I'm going to GDB in quiet mode, ED206. And then I'm going to run with that, and then BBBB. Now it's going to crash. And I might wonder why it crashed. Now, it had some kind of illegal operation at this address, and you can find out what happened this way. There's quite a few ways to do it. This is one of my favorites, 8x10i from EIP-10. And this will just show me the instructions around the instruction that crashed. And it crashed on this command right here. So it tried to move the contents of EAX into the address pointed by EDX. And that was for some reason illegal. So that's the command I'm controlling. And if I look at the registers, and I got to have a single I there. All right. EAX contains B's and EDX contains A's. So I control both of these values. So the B's are the data, and I fed in this junk. So those B's are under my control, and some of these A's went in the other way. So I have a write operation where it crashed, and I control both of those values. So I can now write anything I want in one word of memory. And that's enough to take over the machine if I choose a good place to write. So let's go back to the slides. That's the point. This operation will result in a write operation under my control in the case of an overflow. So where would you write something? Well, you could write onto the stack and hit a saved return border. And then when it returns from that function, we already know how to do that. You can go to the global offset table, which is what we did in format strings, where you have pointers to C library functions. And when it tries to run that library function, it'll go to the code you tell it to. There's the destructors table called when the program exits, and there's more library hooks elsewhere. There's lots of places you can go. So there's an add exit structure. You could hit any function pointer. In Windows, you could easily get to the exception handler, and then when you trigger an exception, it'll hit it. There's quite a lot of places in code where addresses are stored that eventually control execution, and you just have to find one of them that you can get at and take over the machine. So I've got a few cahoots, and then I'll demonstrate more about that one. Cahoots. And I gotta log in here. And this is chapter 5, I think. What is this? Yeah, they want me to pay, but they aren't forcing me to pay yet, so I'm not doing it in a hurry. And this is chapter 5, all right? So my favorites should include 127. Don't need this one anymore. There's, aha, it's not in my favorites. All right, then I got to use this search function, which is pretty good. Not great, but pretty good. Chapter 5. I'm just going to hit these while I'm here. We'll need them next week. There's chapter 5. Okay, good enough. And it's going to randomize, so we're in good shape here. And it's playing music, so life is good. All right. And I even have a place to save the answers. Or the winners, yeah. Oh, just answers. Okay, good. All right. Music seems louder than usual today. Pretty soon they'll switch to the Halloween music, but not yet apparently. All right, got 8 people online and about 6 in the room. Should be a few more coming. Good. All right, guess I'll wait another 5 seconds, see if anybody else is coming. Apparently that's it. All right, so which command will reserve space on the stack? You just declare a variable, and that if it's inside a function, it goes on the stack for that function. All right. What GDB command shows you where the heap is? I don't know if that's better or not. Anyway. All right. info proc map. All right. How do you make a new chunk? Malloc allocates space on the heap, and it returns a pointer to that space so you can use it. Which command will move the EIP to an attacker-controlled value? In Stack Overflows. All right, that's return. When you return from a subroutine, it returns to the stored instruction pointer. That's what we did several weeks ago in the simple Stack Overflow. And which command becomes an arbitrary write after a heap overflow? Free. When you free a chunk, that's when you have to perform a write operation using values that are under the attacker's control. And which one allows direct control of the EIP after a heap overflow? None of them? That's the point. The problem with the heap is it does not normally contain any pointers that go into the EIP. So your exploits get a little more complicated. So Ken, Tan, and Rich, and Virus, I'm guessing is perhaps Caitlin. I think I'm, a chat message is coming in. Oh, Alex. Okay, good. All right, good. I'm glad you told me. All right, good. So I'll save that. And, all right, so let me finish this exploit here I was working on. So I'm going to move this down a little, make it a little easier to see. So what I've got now is I've got the ability to execute a write command. I can, and the command I can execute is, this one, the one this little arrow is pointing to. So I can write EAX into EDX. And EAX is the B's and EDX is the 41. So I want to refine it a little bit more. Let's go back to here and find out which one of these A's controls it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's try that and see what this does. Yes. Okay, now it crashes. Now I want to X like 1I at EIP will do. That's the command, move EAX to EDX, and info registers will show me what's happening. So EAX contains B's and EDX contains BBCC. So it is those bytes that contain the address I'm writing to and these bytes that control the value I put in there. So now I know how to do it. I need to make a Python exploit that will do that. So let's see if I can do that. I'm going to nano A2. I call it A2. And it's going to have shebang, user, bin, environment variable, Python. And I'm going to put this here. That's the stuff. And it was BBCC here. So I'm going to get rid of there. So that's the story. So I'm going to have print that plus EIP. And then a space, and then that. And that should create the string I want. And for first, I'm going to use just a test string so I can tell it's working. 1, 2, 3, 4. And so this is going to be, it's not EIP though, it's going to be destination. I'm going to call it, that's the destination address. just so I know what's going on. All right, so that should do it. Let's see if this works. If I chmod plus x A2, and then I run A2, it prints some reasonable looking stuff. So I should be able to run, instead of using those characters, I should be able to take the output of that command, A2, and let's see what that does. If I run it from the beginning, it crashes, which is okay. And 1i EIP will show me its move EAX to EDX, and info registers will show me that EAX contains BBBB, and EDX contains 1, 2, 3, 4. So it worked. So EDX is the destination address. Now I just need to figure out what a destination I want to put in. And I think, again, there's a winner function I'm trying to hit. So if I disassemble winner, yeah, there it is. So that's the address I want. So let's put that in the exploit. This one. So my destination will be that. All right. So that's going to be putting that junk in backwards. AB 84 04 08. And I'm already wrong because I have to write to a pointer that's going into EIP. This is actually the data, not the address I'm going to put it in. So I'm going to put that over here instead of the B's. Let's save that in the clipboard. It's very easy to get these backwards, and that's why I always do it pretty much by trial and error. Space, then all that junk there. I'm pretty sure that goes there. That is what I want to go into the EIP. So that is the address right. Now I have to figure out where to put it. So to do that, we've been here before. I need to find the global offset table. You can do that with objdump -R for relocation records on ED, I think it's 206. I think it's ED 206. Let's find out if that works. Yep, all right. So now let's list 1 to 50. Let's look at the whole source code of this thing. So it creates this internet structure. It calls the winner. It calls main. That's all pretty normal. Now down here, it does all this junk, and the only thing I care about is it goes to exit. So exit is used here. So if I overwrite the pointer to exit, then when it tries to exit, it'll run my code. So I would like to find the global offset record for the function exit, and that's here. So this is the address I want to write to. And let's put that in the exploit, and then we'll see it go. I see a chat message coming in. Why not printf? You could overwrite printf. You certainly could, and I've done that before in capture the flag competitions and been sorry. The reason you don't want to do printf is because I'm hoping to run this winner function and I won't be able to see the flag. I've made that mistake before. If I nuke printf, I won't see the flag. I will gain control of the computer, but not in a useful way, because once you've overwritten it, it's gone. So that's a very good question. And that's why I actually wrote in the explicit exit in here, so I'd have something. The first time I wrote this program, I didn't have the exit in there, and I wasn't able to successfully exploit it. And that's why we get back to what I was saying right at the start. The vulnerability does not tell you how bad it is. The context tells you how bad it is. I gained some ability to do something to memory, and that may or may not really give me remote code execution, depending on whether I can find a way to turn that into remote code execution. So anyway, this is the address I want to hit. And so if I run this, so this is, that is exit. So that's what goes here, 0C 99, and then 0804. So if I've done it right, which I wouldn't put a lot of money on, this is going to put into the pointer to exit, it's going to put in the address to the winner function. So when it tries to exit, it'll in fact run the winner function. So let's try that. That is A2. So I can go here and just run it again in the debugger and say yes, and it wins. So it worked. It is not a Stack Overflow, but now it ran that and then it crashed because of course it was unable to do the exit. It was off doing something else and it tried to return from the winner function when it thought it was an exit, and of course nothing was set up correctly, so it eventually crashes. But I do manage to control execution and run some of the code the developer put there, which the developer did not expect me to run. So that counts as winning. Anyway, so that is your next job. You'll find them here in the projects. Those two projects are the ones to do. And they're here, ED 205 and 206. You do a heap overflow where you just leak from one variable in the next variable. And this is the one I was really glad to finally have again here, where you can do a realistic heap overflow, where you don't have something ridiculous like a pointer on the heap that's used to run a function. You just have data stored on the heap. Even if that's all you have, you can still take over the machine because you end up controlling a write operation. So, this is the simple proof of concept when it's easy, and this is a more realistic attack when you just have ordinary data stored on the heap. So that's it for heap overflows. I think we're done. Let's see if I got any chat messages. Oops, I hit the wrong button. All right, what's a clean way to pipe down executed winner function to a file? Well, I don't think I know an easy way to do that. For that, you pretty much want to have shellcode. I would, and of course, that would be the next thing. You would have to put your shellcode somewhere, like on the stack, and then run it. And I'm planning to add extra credit portions that do things like that, but we haven't done it yet. Of course, to be fair, it should be pretty obvious how to do it. If you look at this here, you will see, for example, this one here, we ran, if I run this A2, we did inject some series of A's here. Now, this is only about 20 bytes, and you can't do much with 20 bytes. But if we change the parameters so we have maybe a few hundred bytes here, then you could put shellcode here, and that is somewhere in memory. And remember, you can jump to any address you want. So if you could find it, you could inject shellcode and run it, and then you'd have a command prompt and you could do anything you want. And that's, of course, what people really want. So we haven't gone all the way. There's 3 steps in these projects that we've been through. First, you do a denial of service. Then you run code that's already there, which is return-oriented programming. And then you inject code and run it, which is the ultimate goal. And I haven't got this third version in the heap overflow, but you did do it in the format string and the buffer overflow. So I'm thinking I'll add it in as extra credit. I'll just make a version of this with a nice big buffer of several hundred. So there is enough room to put it on a server, and you'll have to take over my server. That's my plan. But I haven't got that project ready yet. But it should be, the rest of it will go just the same as it did in the previous exploits. Any other questions?
Do you know how to do ED203?
ED203? Let's take a look. Yeah, that's a normal buffer overflow. What's the question?
It's not quite connections.
Well, yeah, I'll come take a look at it. I'll see where you are. But this one works, but it's a little tricky. And this is the one, we talked about this before. It does a normal buffer overflow, and then you use Metasploit to make some shell code, and then you inject that shell code and run it. So that's the next step in all these exploits. Once you have the ability to control the EIP, and you have the ability to inject some data, then you inject this special data and run it, and now you get to control the machine. So let me see. I'll take a look at what you're doing there and see if I can find the bug. Any other questions? Well, I'm going to stop the share, and I'll hang around here to help people that want help on projects. Let's do that.